Okay, let's start up again. I got cut off on that last video. So this is the problem. The guy is out here 200 yards away from the shoreline. The marina is over here 600 yards down the shore. He can row at a rate of 3 yards per second, and he can run at a rate of 5 yards per second. And so the question then is, where should he land his boat? Somewhere along the shore here, so that he can minimize the amount of time it's going to take him to get to the marina. Okay, so basically what we want to do is we want to find a function that's going to describe the time it's going to take to travel this distance and the time it's going to take to travel this distance. Okay, so I'm going to do that down here in this bar, and a couple things that I need to know though is what's the length of this red line segment. Okay, and so I can do that in GeoGebra just by going up here and clicking on this thing it's an angle measurement, and then click on that little triangle, and I can find distance or length this way. And all I have to do then is click on here and say this is what I want the distance of, and it tells me that that distance is 2.55. Okay, and then 2.55. I'm trying to grab it, move it. There we go. Alright, so that distance is 2.55. Then I also want to find the distance along the shoreline. And so I just click on the distance again, click on this blue line segment, and I see that that's 4.42. Alright, so those aren't the values that I'm really all that interested in. I'm more interested in how much time it's going to take. Alright, so we're going to go down here and we'll just put in an input line. And I want to take the distance between A and C. Distance between A and C is denoted up here by this lowercase a. So I'm just going to take A, and I know that I can row at 3 yards per second, so the time is going to be that distance divided by 3. Okay, and then I know that I can run at a rate of 5, so I'm going to take this blue distance, which is denoted up here by lowercase b, and just say b divided by 5. Okay, and I'm going to get a function. Okay, that function looks like put it up here as d. So d is 1.73. So it's going to take me 1.73. What would that be? Well, the units on here are going to be in hundreds, so it's going to take me like, what is that? 17.3 second. No, it would be 173 seconds to get to the marina. Okay, and then you can see that as I move this around, we end up landing the boat at different locations. We're going to end up with different times up here, and we want to then find out what's the minimum amount of time. So if I land here, it's going to be 1.86. If I move over to here, that's going to be decreasing, and it looks like it decreases down to about 1.73 is the minimum somewhere in here, and then it starts to increase as we move out this way. We're spending too much time rowing and not enough time running here. Okay, so then the question then is we want to optimize this. So what I want to look at is there's a function that gives me the value of, we'll say, the x-coordinate of C, and then I want to look at how that's related to D. Alright, so let's just plot a point, and we'll just go up here and grab a point, plot it somewhere up here. That's point E. We're going to grab that point, right click on it, and we're going to say, give me the basic information about this. And what I'd like to do is the same thing I did on that last video, was I want the x-coordinate of this point along the shoreline, which is C. So I want the x-coordinate of C. And then the y-coordinate I want to be the time that it takes for me to get to the marina, which was, we did over here was lowercase d. Okay, so we'll just plot this as d and close it. Alright, so this point E, the vertical distance above this point is how long it's going to take me to get to the marina if I land the boat at some distance x along the shoreline. Alright, and you can see that that function doesn't really change a whole lot, but you can see it dips down and then it goes back up again. Alright, and so what I'd like to do then is we'll trace it. So I'm going to right click on it again, and we'll turn the trace on. And again, it looks like it's decreasing until I get to a certain point, and then it kind of flattens out, and then it starts to increase again. All right, so this is the underlying function that I want to optimize. Okay, so we need to come up with what that function is. So let me switch over to my camera. And we've got a situation where this is 200 units out here along the away from the shoreline. The marina is over here at 600 units down the shoreline. We're going to land our boat someplace, and we'll say that that's X. We're going to row this far, and then we're going to run this far. Okay, so we need a function for time, and so this distance is 2, this is X. The length of the hypotenuse is going to be the square root of 4 plus X squared. Okay, and so that's the distance that we're going to row, and so the amount of time we're going to spend doing that is going to be 1/3, because we can row at a rate of 3 yards per second times the square root of 4 plus X squared, plus the distance from here to here. Well, that's just going to be 6 minus X, and so 6 minus X, and then we're going to run at a rate of 5 yards per second. So this is the time that it's going to take me to get to the marina as a function of X. Okay, so next thing we do is we're going to find out what's the minimum value of this function. So we got to take the derivative, and so t prime of X. Now if this is that to the 1/2 power, we're going to get 1/3 times 1/2 4 plus X squared to the negative 1/2 power times 2X plus the derivative of this is going to give me just negative 1/5 X. Okay, and then let's just clean that up a little bit. The 2X and the 2 are going to cancel each other out. This is going to give me X in the numerator, 3 square root of 4 plus X squared in the denominator, and then minus X over 5. All right, and then of course we want to find out where that's equal to 0. Okay, now I'd like to be able to avoid the algebra on this one and show the students another way that we can optimize a function by looking at the graph. Okay, so I'm going to take this function and I'm going to plot it in GeoGebra. Okay, remember this is the derivative, not the function. Okay, so go back to GeoGebra, and I'm going to plot or just graph that derivative. Okay, so it's t of x is x divided by, and then in the denominator I've got 3, and then times the square root, and square root is just going to be times sqrt, and then what we're going to take the square root of is 4 plus x squared, 4 plus x squared. Okay, and then we're going to subtract from that 1/5 x, or just x divided by 5. Actually, that's not right. I need to go back here again. This shouldn't be x over 5. That should be, the derivative of that should be 1/5. Okay, so minus 1/5. Okay, so we'll go back to GeoGebra again, and we're going to subtract not x over 5, but 1/5. Okay, so remember this is the derivative, not the function. So I graph it, and what I'm really interested in is where does that derivative take on the value of 0? And so if I zoom in on this point, I can see that it looks like it crosses somewhere in between there. GeoGebra is kind of nice because I can tell it that I want to put an object at the intersection of two things. Okay, so I want to find out where does this curve intersect the x-axis. And it says it does it right there at the point F. Okay, and it says that F is 1.5 and 0. Okay, so it looks to me like we're going to optimize our value of the function when x is equal to 1.5. Right, now, hopefully you're telling your students that just because we found a critical point doesn't necessarily mean it's the answer to the question. This gives us an opportunity to look at, this is the derivative. The derivative is equal to 0 at 1.5, but over on this side, the derivative is taking on negative values, and then the derivative is taking on positive values, which means by the first derivative test, this is going to be a local minimum. The function is decreasing, then the function is increasing. Okay, and if we go back up to where we traced that, okay, so here we've got the trace of that point up there above is really the function that I'm trying to model, and it's going to be decreasing until I get to that point, and then it starts to increase again. All right, and also notice that it doesn't increase or decrease with a very quick pace because this function is not increasing very quickly. Okay, it stays pretty close to zero. All right, so hopefully this gives you some tools that you can use in your recitation sections that is maybe a little bit beyond just going through homework questions. Maybe give the students a little bit different perspective on solving some of the problems or using some technology to do it. You might encourage your students to go ahead and download the GeoGebra software too. It's a nice way to do some investigations and just maybe satisfy some curiosity they might have in solving more problems like this. Okay, if you have any questions, feel free to give me an email or just stop in my office and let me know. Hopefully you will take advantage of this, do what you want with it. I know that you guys have got a lot of time that is dedicated towards your own schoolwork, but I think this is kind of a cool thing, and I think you might learn some mathematics by playing around with it yourselves. Okay, thanks, and have a great rest of the week and a great weekend.